Hey folks, how's it going? This is Rob coming to you with a video on homework quiz number 5 for Math 134, Spring 2020 semester. So in this video, I'm going to walk through the homework quiz, just recapping the directions. You're only doing 1 and 2 or 2, either one of them. Remembering if you did both, I would grade just the first one, and then you got to do the one on the back. All right, and so this homework quiz covered optimization and kind of the basics of integration. Okay. All right, here we go. So Smile and Sam's Super Soup Shipments has a 1,700 yard of material with which to enclose its new warehouse. What are the dimensions of the largest area that can be enclosed, and what is that largest area? Okay, so first of all, we're given area, and the fact that we have material is going to indicate that there's something related to perimeter. So what we know, let's say that x is the length and y is the width. So we have 2 times x plus 2 times y is 1,700, because we take the twice the length, 2 of the lengths, right? You can imagine we have this little shape right here. 2 of the lengths plus 2 of the widths has to be the whole perimeter of 1,700. And we know that area is equal to x times y. We don't know what the area is, but this is what we want to maximize. Okay. Now, we don't have, you notice how in the thing we want to maximize, we have 2 letters. So we don't have any strategies for dealing with that. And what I'm going to do is I'm going to get y alone here. That's my choice. You could get x alone as well. It doesn't really matter, but I'd rather do derivatives with x's in them than y's. Again, it doesn't matter as long as you get it right in context. So what I'm going to do is I'm going to minus 2y from, I'm going to get, y alone. So I'm going to minus 2x from both sides. When I do that, I get 2y is equal to 1,700 minus 2x. And then I divide by 2, and I get y is equal to 850 minus x. All right. Because 850 is half of 1,700, and like right, 1 is half of 2. All right, and now I'm going to make a direct substitution. So a is equal to x, and since this is y, instead of writing y, I'm going to write 850 minus x, right? Because the point is to get it so there's only x's. So it's equal to 850x minus x squared. Okay. And now I'm going to take the derivative of this. So the derivative of this with respect to x is equal to minus 2x plus 850. I'm going to put my x's first. And so the maximum value that represents the width is going to be what I get when this is 0. Now, technically, the width can be as little as 0 or as much, now you got to be careful here, as 850. You can't be 17, because if it's more than 850, right, if the length is more than 850, then the width, okay, is going to be a negative number. Okay, and we can't have that. And technically 850 shouldn't even count, because that would make the area 0, because the width would be 0. But it's worth trying. Now, we need to set this equal to 0 and solve, because remember, the critical numbers, that is, the numbers that make the derivative either 0 or undefined, represent our potential maxes and mins. Now, in this case, because it's a polynomial, right, it's a line, there are not going to be any things that make it undefined, right? A line is continuous everywhere. So I add 2x to both sides, so 2x equals 850. I divide by 2, and I get x is equal to 425. Beautiful. All right. And now what I do is I come back in and I plug in here. So that's the length. The width is equal to 850 minus 425, which is 425. Okay. So the maximum dimensions are that the length is 425 and the width is 425. And if you want to know what the actual maximum area is, okay, what you would do is you would take those dimensions and you would actually then plug them back into the area and calculate. Okay, so that would be 425 times 425, and I'm going to use my calculator here. and I get 180,625. Now this is why you were allowed to, partially why you were allowed to use a calculator. And actually, what's our units here? This is square yards. So technically we should specify this is yards and this is yards. Okay, but in any case, this is why I let you use a calculator, because I wouldn't ask you to do 425 times 425 without a calculator. All right, so if this is the problem you chose, and I believe everyone chose this, please make sure you understand this. But then in a minute, I am going to go ahead and move on to the next problem. All right, now Malevolent Marys. So Malevolent Marys makes magnificent flower boxes by cutting out a square from each corner and folding the corners up. It costs a cent per each square inch of material. If a standard box is 20 inches long and 15 inches wide, find the dimensions that minimize the cost of the material. What is the minimum cost? Okay, so again, let's highlight what we know. We know this, standard thing, this. Okay, so here's what it looks like. Let me just get a little square tool here, a little rectangle tool. So I've got this box, right? And what I'm going to do is I'm going to cut out a corner of each side. And you'll have to forgive me. These are supposed to be all squares, and the length and width of the squares is to be the same. For example, this length is the same and this width is the same, and it's equal to all of these. So in other words, suppose that dimension is x, and it doesn't look like they're all the same. So we're going to forgive my Rob's bad artwork here. We're going to pretend they're the same. And so what I'm going to do is I'm going to cut those corners, and then I'm going to fold up the sides. So it's going to look like something like this. If I can do a little like 3D. So see, the sides fold up. Okay. You can imagine maybe like the flowers going in there maybe. Okay. This is me trying my hardest to do a little 3D drawing here. Okay. Here's my 3D box. Okay. And this height is X, etc. So we're going to fold it up. Now, here's the other thing we know. We know that this is not the full length anymore. So we had to sacrifice some of the material. So though this was 20 inches long originally, this new piece right here, if we think about this piece, this blue, right, this is going to become 20 minus 2x, because I take the whole length of 20 and I cut out that 2x. And similarly, this is going to be 15 minus 2x. Okay, so again, if we translate this, this is 20 minus 2x. Now, we can assume that this box has an open top, because there'd be, if you think about it, there's no way to stretch that material and make a top to it. So here's what I know. I need to do the surface area. So I know, let's cut this up. I've got 2 of these. Alrighty, I know I've got 2 of these. And then I know it's tough to see, but I then also have 1 of these bases. Okay? So the base is 20 minus 2x times 15 minus 2x. Okay? So I've got 1 of those, then I've got 2, and I've got 15 minus 2x times x. So actually, let me just back up a second. Let's do that in blue, because that represents the blue part. So it's not a volume problem, folks. It's a surface area problem, because that's what we're trying. We're trying to find the minimum surface area, trying to minimize the surface area. Okay, 15 minus 2x times x. So we have, I guess to be technical, I really should have done this in green, because this is the green pieces. Okay, so forgive me there. And now for the purple pieces, I have 2 times 20 minus 2x times x, right? Because there's 2 of them, and that's the length and the height, okay? So we do have to do a little bit of simplification here. So let's try to do some expansion here. So I've got 300, and you could, again, you'd use your calculator for this. So 300, I'm gonna be a little bit more careful with that. 300 minus 40x minus 30x plus 2x squared, 4x squared. Remember, we want our x squareds to be a positive number, because if our biggest, it will be an x squared, but we want it to be positive, that value, because that will ensure we have a minimum, and that's what we're looking for. Okay, here I'm gonna get, so if I distribute this, I get 30 minus 4x, so I'm gonna get plus 30x minus 4x squared. Alrighty, and then, and this might end up being a maximization problem, or well, it doesn't. We'll think about that. Alrighty, so I now have to do this one, and it's going to be 40 minus 4x. So what I get is plus 40x minus 4x squared. Okay, so that's what I get when I do out everything. So now it's time to combine like terms. So I have, if I combine the x's, you can see the 40 and the 40 will cancel, and the 30 and the 30 will interestingly also cancel, so that will go away. So see, the 40 will cancel with the 40, the 30 will cancel with the 30. Okay, the 4x squared will cancel, so I've got essentially negative 4x squared plus 300 is my function. I take the derivative, and I'm going to make it 0. Okay, so the derivative with respect to x is equal to negative 8x plus negative 8x, actually, because the 300 goes away. Interesting. All right. So basically, and this is not like a super stellar problem, because the other thing, right, is, so we need to find the minimum dimensions, and so that's going to be important, okay, because we need to minimize our surface area here. Okay, and we know this box doesn't really have a top to it. So long story short, if, assuming that I did everything right here, which it looks like I did, what I'm going to do is I get my final surface area. It's crazy, though, how much stuff cancels, right? When you think about it, how much stuff actually canceled out right there. Okay? I wouldn't worry about it too much. What you end up getting is, right, your critical number has to be, so you get a critical number of 0. Then you also know that x has to be between, okay, well, it can't be more than 7.5. So it's got to be at least 0 for context, and it's got to be no more than 7.5. Because if it's more than 7.5, this becomes 0. Okay? So in all likelihood, right, we notice that the critical number here, the critical number is 0. So we would try that. So we would get 20 and 15 are those dimensions. Okay, giving us 300 square thing. And then if we do that at 1 cent each, I believe that would give me $3. All right, I wouldn't worry too much about this one. This was not like the best question, partially because I kind of made this up on the fly. And the good news is people mostly stuck to the first one. But on the midterm, I definitely am going to make sure that the question works out a little bit nicer than that. So don't worry if you didn't understand number 2. I would worry mostly about setting up the problem and making sure you understand the relationships for these ones. Okay, so if needed, please go back and rewind and make sure you understand. And then in a moment, I'll move on to the integration. All right, integration. So we need to solve the initial value problem. So here's the idea. Whenever you integrate, you're always going to have that plus c on the end when you're doing rather an indefinite integral. That leads to something and you're going to have a c on the end. When I give you the initial value, what that does is that actually helps you solve for c and it gives you a specific solution. So what I'm going to do is I know that f of x is equal to the integral of, right, the derivative, right? And so what I'm going to do is I'm going to do that. So I'm going to do the integral of 1 plus 1 over x squared with respect to x. And I'll break this up piece by piece. So the derivative of 1 with respect to x is x. And you could view 1 over x squared as x to the negative 2. So to make sure this works, I need to have this needs to be negative, this needs to be x, and this needs to be to the negative 1. And the reason that is because when I do the power rule, this comes down, turns this into a plus, and then the exponent drops down by 1 and becomes a negative 2. And because it's a negative 2, you get 1 over x squared. And then you add in the c, because it is an indefinite integral, and whenever you have an indefinite integral, there's a potential that there was a constant of integration, because remember, when you differentiate a constant, you get 0. So that's what I'm getting at. We don't know that there wasn't a constant here, because there could have been one, and then when I differentiated it was 0, so it wouldn't have shown up in the actual derivative. Okay? So in other words, this is equal to 1 minus 1 over x squared, or rather 1 over x. 1 minus 1 over x plus c. Now, to figure this out, what we know is that since f of 1 is 10, 10 is equal to 1 minus 1 over 1 plus c, which is equal to 1 minus 1 plus c, which is equal to c, because these cancel. So c is equal to 10. So the final function you write is f of x is equal to 1, or rather this should be x. Should be x. It's only 1 when you plug it in. My mistake. So you get so final function is f of x equals x minus 1 over x plus 10, or f of x equals x minus x to the negative 1 plus 10. Those are mathematically equivalent, so I will take either one. To check our work, we could differentiate. So if I differentiate this, notice that I'll do this in red or green to check my work. So the derivative of this with respect to x, the derivative, not negative 1. So the derivative of x is 1. Here I bring down the 1, it cancels and gives me a 1, or rather a positive, my mistake, positive 1. And then the power drops to 2, and the 10 cancels. So I get 1 plus 1 over x squared, and that's exactly what's inside here. Okay, so answers to this, either one of these will be acceptable. Okay, I'd prefer the first, but the second is technically equivalent from a mathematical perspective. It's not really simplified, but I guess if I don't ask you to simplify completely, it's tough to really mark you down for that. So again, prefer the first. They're technically both mathematically equivalent, but again, prefer the first. So hopefully you found this video to be helpful and to really lay it out. Remember that the key ideas are for optimization, finding the relationships, using the relationships to solve the problem. And then for integration, remembering our rules of integrals. You could have broken this up using the sum rule and the power rule if you wanted. It's your choice. But the idea of working backwards and using an anti-differentiating, thinking about what, when I differentiate it, gives me the thing in the integral. Okay? And then using the initial value to plug in and find the answer. Okay? So thanks very much. Hopefully you found this video to be helpful. I encourage you to check out any of the midterm review resources and resources on Blackboard. Keep it up. Don't forget to love math. And remember, you can do it. All right, thanks much. Looking forward to seeing everyone next week in the classroom, online, and have a wonderful day.